Okay, datum target simulation effects. The datum features, target areas, target lines, and target points all have different simulation methods. Okay, the different effects on simulated datums is relative to a datum feature. There's little difference if the datum feature surface variation is small. But if it's big, yeah, there's a big difference. You can affect your tolerance of that simulator. A physical simulator sized to the contact all of the surface to establish a simulated datum plane, and virtual simulator point data collected across an entire feature or area to create a simulated data plane. Those are different methods. Okay, the effects of datum feature simulators. And on the left, these are some of the examples in the textbook. There are more. But uh, we have examples of a datum point on a surface with C1 in the first left, and they've got a spherical pin or tooling ball that's touching it in the side view. And it has to be a zone that's measured with a tolerance in each axis of the plane it simulates. And then we have our datum target line simulator. It gives you a little more freedom to build your fixture. It just has to hit somewhere along that line. And then over on the right, we have a datum simulator that's an area. So you have a crosshatched square and that's allowing a square shaped tooling feature to contact anywhere in that area. And a datum feature simulator example is this block. So maybe you put a 1, 2, 3 block up against a surface so that you can measure the distance to somewhere with a specific tool, and you're actually measuring against the 1, 2, 3 block and not the actual piece to get the measurement workpiece. That becomes a simulated datum in itself. Okay, and so when you just have a datum call to a surface, it's that entire surface and not a target. So that last example on the lower right is not a datum target. It's a datum feature. And it becomes simulated when we put something up against that surface to use it to measure or locate the part. Okay, large surface variation in actual contact. Target point simulators located to contact the target on a perfect feature. Simulator may not contact imperfect features at exact intended location, and the simulated datum passes through the simulated point. The simulated datum may not pass through intended target on an imperfect feature. And additional feature tolerance is needed if difference between the point of contact and the simulator is significant to the tolerance. So this would be an example of I put something on my desk and try to use the desk as a surface plate. That's going to affect my measurement of anything I use, for say, for a height gauge. That's one reason we use precision ground inspection plates so that we're trying to eliminate the tolerance of the simulated datum proxy, if you call it, from affecting our measurements. Okay, we're going to establish datums and datum reference frames from datum features. Okay, so datum features are on the part, use the established datums. Simulated datums, establish them through data simulation with a contact with something other than the part itself. And features may be flat surfaces, features of size, feature of shapes, and patterns of features. The order of precedence and applicable material boundary matters, and the datum reference frame created from the referenced datum features. A datum simulation. Simulation in industry is essential because fabrication and inspection operations made in relationship to specified datum features may affect the tool quality piece of hardware and computer calculations through CMM or NC machines. NC machines, I mean CNC machines, but there's a subtle difference. Establish simulated datums by approximating the theoretical location of the datum from imperfect datum features. Okay, so say you had a cast bowl and it has 3 feet on it, and you can reliably say, okay, well, these 3 feet are cast, so they're irregular, but I want those to be my datum features, and I clamp it to a table. A table becomes our simulator of tooling to make that flat so that I can say machine the top of the cast iron bowl parallel to where the feet contact our simulated datum, being the table of the machine. Okay, precise methods. So difference between simulated datums relative to theoretical datums, and insights for tolerance values. So you need to be careful on how you choose to use these methods. Okay, material boundary modifiers. So we've talked about material condition, which affects the finished feature tolerance of size, but the datum feature reference applies regardless of material boundary, RMB, if there isn't a modifier. So that's with the boundary itself of the datum having variance in its surface. Okay, simulator at a fixed size if allowed by the modifying symbols. So at maximum material boundary, or at least at material boundary. So your fixture would need to accommodate the part at those 2 different conditions. And apply to the datum feature references when material boundaries exist. So regular features of size always have at least 1 material boundary. And surfaces and irregular features of size have material boundaries when profile tolerances are applied. Okay, interrupted surfaces as datum features. Interrupted surfaces establish a single datum feature by applying the profile tolerance and the datum feature symbol. So in this example, we have 3 faces, and that profile makes up a datum, and the symbol, by having 3 times there, is letting you know that there's 3 contact surfaces that make up that datum A in our example on the left. The number of surfaces noted on the feature control frame if multiple, and the datum feature must be referenced in the feature control frame or a note for its identification to be relevant. Okay, so I see a lot of companies probably should be doing this, and they don't. They just leave it up to be assumed that those lines are continuous. Order of precedence. Established from reference order in the feature control frame. Okay, it's not alphabetical. And 2 tolerances are related to the same datum reference plane. Okay, there are 2 feature control frames reference the same datums in the same order of precedence with the same material boundary modifiers. And it's the only time the reference frames, and again, when I'm talking reference frames, is different than the feature control frame. The datum reference frame is actually the physical 3 planes that make up our translational control. And what this is saying is the only time you use the same exact feature control frame for 2 different tolerances is when the datums are called in the same order and they're using the same exact datums. Otherwise, you end up with 2 different frames. So when two tolerances establish separate datum reference frames, the datum reference frame A, B, and C are different from D, E, and F because they are different datum features. And reference frame A, B, and C is different from B, A, C because the order of precedence is different. So the only instance where the actual references on the part would be identical is if the call out on the feature control frame is identical. Okay, typically flat primary datums. The first datum feature is referenced in the feature control frame. So typically that's your first one. It establishes the primary plane, and it's located by a minimum of 3 highest points on a surface. And the point locations unknown and cannot be predicted. Then a simulator plate must be as large as the datum feature, and the workpiece must be stabilized on that primary plane. 3 of the 6 degrees of freedom are constrained, 1 translational and 2 rotational. So think of it as, okay, I've established my primary datum feature, I put something on a table, and I can slide it and I can turn it on that plane. So I've only controlled in linear axis, 1 axis, and you can't spin it in the axes that it's stuck to. Okay. Okay, the flat secondary datum feature. Second datum feature references in the feature control frame, so it would be in the second box. Establishes a secondary plane perpendicular to the first one, the primary plane. And it's located by a minimum of 2 highest points on the surface. Point locations unknown and cannot be predicted, and 1 rotational and 1 translational degree of freedom not previously constrained by the primary datum are now constrained. Okay, so you've now constrained it, say sliding one direction, and it can't spin in another direction. Okay, and the primary and secondary datums constrain 3 rotational and 2 translational degrees of freedom. And this is why we need the flat tertiary datum feature. The third datum feature reference in the feature control frame establishes a tertiary plane perpendicular to the primary and secondary planes, located by a minimum of the highest point on that third surface. And the point location again also is unknown and cannot be predicted unless you're going to use targets. And 1 transitional degree of freedom, not constrained by the primary or secondary datums, are now constrained. So once you have 2 datums, you can't rotate it. It could still slide back and forth in 1 axis, and that's what this third one is. So using the vise example, you've got your part in your vise and you haven't clamped it yet, and you can slide it all the way back and forth in any position until you put a work stop in that's going to touch 1 point to keep it from sliding back and forth. That'd be your tertiary datum. And all rotational and translational degrees of freedom are constrained at this point. Okay, datum simulation of flat features. So if you have an imperfect simulation method to determine simulated datums and locations with adequate accuracy for the setup. Okay, so you're saying, okay, I'm now involved the granite surface plate that's ground to a different tolerance, so it's not going to be as accurate as the actual plate, but it's within the tolerances of what I'm working to. And it's meant to locate a datum on a basis of a workpiece datum feature. Variations on a datum simulation tool or process can result in a small amount of datum simulation error. It may result in the measurement inaccuracy that might impact fit or function. Okay, so material boundary modifiers on a flat datum feature. All datum feature references assume to be applied at, regardless of material boundary. Secondary or tertiary flat datum features having boundary conditions may apply MMB or LMB for maximum material boundary or maximum or least material boundary. Okay. Only when geometric tolerances establish material boundaries on those datum features. And MMB or LMB are never applied on a primary datum feature reference for a flat surface. So it looks like you're allowed to use them on the secondary and tertiary. So we look at the example on the left. Our primary datum is A, which typically is going to be the flat surface of the face where it's called out, and then they're calling datum C at least material boundary condition, and it shows the zone of least material to maximum, and your gauge has a range, and with it which it can affect the part. So your gauge or fixture needs to be designed so that the simulated contact point can make maximum contact within the range of MMB or LMB. Okay, secondary or tertiary datums feature referenced at RMB. The datum feature simulator progresses from maximum material boundary toward least material boundary. The simulator makes maximum contact with the datum feature. Okay. Secondary or tertiary feature referenced at maximum material boundary. The datum feature simulator in the fixed location is going to be made in the fixture at maximum material boundary. Okay. So your simulator in this case would be if that 250,000th dimension is at its maximum material boundary, so the most amount of material on that. So the simulator needs to be fixed at a location of 240 thousandths. So we're assuming this has a plus or minus 10 tolerance on that location. Okay, the datum feature is not required to contact the simulator. Okay, cylindrical features. Shafts, holes, counterbores, and other cylindrical items may be identified as datum features of size. Datum feature symbol applied clearly to feature of size and not the surface, and do not place on an extension line from the surface. So on the left, we show different displays. We have a model on the left with the datum feature pointing at the circle, or it could be applied to the dimension extension line. On the right, we have two more variations. In a orthographic view, you can have the additional attachment of the triangle being on the cylindrical feature edge. In this example, we have associativity determines one hole or both holes establish the datum. And on the right indicates the pattern of the feature establishes the datum. So there's a difference in which way you approach you would use. Okay, interrupted cylindrical features. Interrupted features act like a single feature in a design application. Continuous feature symbol applied indicates a single feature. Interpretation could be as multiple features without the CF symbol. So in this case, in the left, we have a dimension that applies to a diameter, and it used to be implied that it would carry on to the next diameter. But technically you should have the CF symbol if you intend that tolerance to apply to both zones next to either the datum or the dimension itself.